Diastereoisomerism. Diastereoisomers or diastereomers are the stereoisomers which are non-superimposable but not related as mirror images. So the diastereoisomers are non-superimposable stereoisomers and not related as object and mirror image. And one of the criteria to become a diastereoisomer is must possess at least two stereogenic centers. So at least possess two stereogenic centers. For example, 2-bromo, 3-chloro-butane. So here I am going to draw the structure of 2-bromo, 3-chloro-butane as like this. 4 carbons are there. So here in the second carbon, I am going to write the bromine in right side and the hydrogen is on left side. And in the third carbon, chlorine is on right side and the hydrogen is on left side. So here two stereogenic centers are there. One is this and the next one is this. So to draw the next stereoisomer, to draw the next diastereoisomer, I am going to fix these three groups here. That is, in the first stereogenic center, I am going to fix bromine on right side, hydrogen on left side, and the CH3 on the above initial projection structure. So to draw the second structure, so these groups are fixed. And in the second stereogenic center, I am going to interconvert the position of these two groups. That is, chlorine is on left side and hydrogen is on right side. And CH3 on the bottom. So these two are the diastereoisomers of 2-bromo, 3-chloro-butane. Here, one of the chiral center opposed its configuration, and in the next one, the configuration is identical. Okay, that is, in one of the chiral center, the position of the groups are interchanged, but not in the second stereogenic center. Then, if you talk about the properties of diastereoisomers, the physical properties as well as the chemical properties of diastereoisomers are entirely different. So, physical properties such as melting point, boiling point, and solubility, etc., are different for the diastereoisomers. So from this, it is clear that the diastereoisomers are easy to separate. So we can separate this diastereoisomers by using simple methods, simple physical separation methods like fractional distillation, or fractional crystallization, etc. So since the physical properties of diastereoisomers are different, we can easily separate these isomers by using simple physical methods like fractional distillation, fractional crystallization, etc. And if we study the chemical properties of these compounds, their chemical reactivity towards some reagents are different. Their chemical reactivity is different. So if you talk about the optical activity, we cannot say all the diastereoisomers are surely optically active, but in some case or in some diastereoisomers are optically active and some are not. Okay, some of them are optically active and some of them are not active. That we will discuss later in this section. From the last video, you may be clear about enantiomers. So now we are going to differentiate enantiomers and diastereomers. So enantiomers are optically active mirror images, or enantiomers are non-superimposable mirror images. But in coming to diastereoisomers are also non-superimposable, but they are not mirror images. So we can write here they are mirror images, but here not mirror images. Then coming to the physical property, their physical properties are same. But here physical properties are different. So since the physical properties are same, they cannot be separated by simple methods. Simple physical methods like fractional crystallization, fractional distillation, etc. But they are isolable. Anyway, isolable but cannot separate by simple methods. Okay. But coming to diastereoisomers, their physical properties are entirely different, so it is easy to separate by using simple physical methods. Can use simple methods to separate the isomers. Okay. Then if we talk about the optical activity of these two isomers, these compounds, that is enantiomers, are surely optically active. But here we cannot surely say that these compounds are optically active, but we can say these may be optically active. Then if we talk about the rotation of plane polarized light, if one enantiomer rotate the plane polarized in clockwise direction, and then the next one will rotate it in anti-clockwise direction, and we already told that the magnitude of the rotation will be same, only their direction will be different. Okay, so here rotation, extent of rotation is same. Extent of rotation is same, but sign is different. One is plus and the next one is minus. But coming to diastereoisomers, they maybe rotate the plane polarized in same direction, or maybe rotate them in opposite direction. And the fact is that the extent of rotation is also different. So we cannot say only differ in sign. The extent of rotation is also different. So here the extent of rotation of plane polarized light is different. Then if we talk about the sign, they may be same or may not be same. Now let us learn the DL configuration of organic molecules. So configuration means represent the spatial arrangement of groups around a chiral center. So spatial arrangement of groups around the chiral center is known as configuration. D and L configuration means D and L configurations are actually relative configuration. That is, these configurations are represented by comparing the molecule with the glyceraldehyde. That is, we are representing the configuration of the given molecule or the given stereoisomer by comparing the isomer with the glyceraldehyde. That is, comparing the isomer either with the D-glyceraldehyde or with the L-glyceraldehyde. So actually the structure of D-glyceraldehyde is this: CHO, CH2OH, OH is on right side and hydrogen is on left side. And the structure of L-glyceraldehyde is this: CHO, CH2OH, this is D plus glyceraldehyde and this is L minus glyceraldehyde. So if we have any enantiomer or any stereoisomer, then first of all we compare the stereoisomer with these two structures. So any compound that could be obtained from D-glyceraldehyde or any compound or any stereoisomer that could be converted into D-glyceraldehyde is belong to D series. And any isomer which is converted to L-glyceraldehyde or L-glyceraldehyde or any isomers which could be obtained from L-glyceraldehyde is belong to L series. So we can say D series is any compound that could be obtained from D-glyceraldehyde and the basic structure is this. And L series is any compound that could be obtained from L-glyceraldehyde and the basic structure is this. Then erythros and threos. Erythros and threos are the diastereoisomers. They are diastereoisomers. D and L series of erythros and threos structures are there. Actually, erythros means in a stereoisomer, if both the same groups are on same side, then it is categorized as erythros. For example, if we talk about the erythros and threos structures of aldotetros, erythros is like this: CHO, aldotetros, 4 carbon groups are there and 2 stereogenic centers are there, 1, 2. In here, both the stereogenic centers are attached to one OH group and one hydrogen group. So here OH is on right side and hydrogen is on left side. In erythro structure, both the same groups are on same side. That is, here also OH is on right side and hydrogen is on left side. While in trio structure, same groups are on opposite side. That is, here OH is on right side and hydrogen is on left side. while here hydrogen is on right side and the OH is on left side. Actually, these two are the structures of D-erythrose and D-threose. This is D-erythrose, D minus erythrose and D minus threose. Why it is categorized as D-erythrose and D-threose? Because if we look at the structure, we can clearly say that this group is derived from the D series. Here is the D series. Same way, this is the D series. So these two are D-erythrose and D-threose. So if you draw the structures of L-erythrose and L-threose, that will be the mirror image of these two. So if we draw the structure of L plus erythrose, the structure will be the mirror image of this one, that is CHO, C, OH will be on left side and the hydrogen is on right side, C, H on left side and OH is on right side, then CH2OH. So this is the L plus erythrose. So this is the mirror image. These two are the mirror images. And if you check the series, this is coming under L series. Right. So this is L erythrose and this is D erythrose. Same way, the mirror image of this will be the D threose. That is D threose is this CHO, CH on left side, OH is on right side, and the C here OH is on left side and hydrogen on right side, and here CH2OH. Actually, the erythrose and threose structures of aldotetrose are prepared from D-glyceraldehyde by a process known as Kiliani reaction.